Hello and welcome. Today we're going to talk about a Nobel Prize winning discovery that really challenges our basic ideas about how the world works. It's a story that asks a really profound question. What if the bizarre, strange rules of the atomic world could actually govern an object you can see and touch? So let's just frame our whole discussion around this one central question. Can the weird, counterintuitive rules that apply to a single atom also apply to an electrical circuit? Something big enough for you to actually hold in your hand? For the longest time, physicists would have told you absolutely not. But as it turns out, a groundbreaking Nobel Prize winning discovery proved that thinking completely wrong. All right, so where do we begin? Let's start with the big award this work received. This is Section 1, a Nobel for quantum leaps, and a little bit about how scientists managed to observe what was once thought to be impossible. So, the 2025 Nobel Prize in Physics went to a group of scientists for something truly mind-bending. They actually observed quantum mechanical effects on a macroscopic scale. Now, what does that mean? It means they took these strange principles from the quantum world, the ones we thought were locked away in the subatomic realm, and they showed them working in a tangible, human-made object. This prize was shared by three scientists whose work was just deeply intertwined. Think of it like a relay race. First, you had John Clarke, who was a real pioneer, developing the fundamental superconducting devices. Then, building on that foundation, Michel H. Devoret came along and made these huge advances in actually controlling the delicate quantum behavior inside these circuits. And finally, John M. Martinis was the one who actually built the devices, the superconducting qubits, that put it all together to demonstrate these quantum effects on a massive scale. So, here's the crucial takeaway, the big idea. Their shared discovery proved, once and for all, that the fundamental rules of quantum mechanics can govern a large engineered system. This wasn't just a small finding. It completely shattered that old idea that there's some kind of invisible wall between our world and the quantum world. So how in the world did they actually prove this? Well, it boils down to two key quantum phenomena they managed to observe. Let's tackle the first one, which is really like a quantum escape act. Section 2. Tunneling on a grand scale. Okay, first, we need to understand a core concept here, quantum tunneling. Now, in our everyday world, if you try to roll a ball over a hill but don't give it enough of a push, it's not going over. It's trapped. Simple. But in the quantum world, things are different. That particle has a very real, measurable probability of just disappearing from one side of the barrier and reappearing on the other without ever having had the energy to go over it. And this is where the sheer scale of their discovery really hits you. On the left, you've got our classical intuition. A ball hits a wall, it stops. A current hits an insulator, it stops. But look at the right. This is what they saw. It wasn't just one little electron sneaking through. We're talking about an entire electrical current, billions and billions of electrons, all acting together as one single quantum thing, tunneling through a barrier that, by all classical accounts, should have been a dead end. So, how they do it? Let's walk through the steps. First, they took a superconducting circuit and cooled it way, way down to near absolute zero. This is crucial because it makes the entire current behave as a single, coherent quantum entity. Second, they watched as this current circulated with zero voltage. Classically speaking, it was trapped in that state. It had no way out. And then, third, the magic moment. They witnessed the entire system, the whole current, simultaneously tunnel through its energy barrier into a totally new state, one where a voltage suddenly appeared. It was a quantum leap, but visible on a device you could see with your own eyes. Okay, so that tunneling was one half of the story. The other half is just as wild, and it led to the creation of something called an artificial atom. That's Section 3, the artificial atom circuit. This next part is all about another cornerstone of quantum mechanics, something called energy quantization. The basic idea is that energy isn't smooth and continuous like a ramp. It's more like a staircase. An atom can only exist on specific energy steps, these discrete packets called quanta, and it simply cannot exist in the space in between. And this is what they built. It's absolutely brilliant. Think about a real atom, right? It has these very specific, fixed energy levels. Well, guess what? Their electrical circuit also had specific quantized energy levels. A real atom jumps between these levels by absorbing or emitting photons. Their circuit? It jumped between its levels using that macroscopic quantum tunneling we just talked about. In every meaningful way, they had built a large-scale, artificial atom that followed the exact same quantum rules. So, what was the secret sauce? What's the one piece of technology that made all of this possible? It's called the Josephson junction, and it sounds almost ridiculously simple. It's just a very thin layer of insulating material sandwiched between two superconductors. But that tiny component is what forces the entire circuit to behave as a single quantum object and enables all of these incredible macroscopic effects. All right, so this is obviously a huge deal for physics, but you might be wondering, okay, what does this actually mean for us, for the technology we use? Well, that brings us to our final section, building the quantum future. You see, this wasn't just some abstract experiment in a lab. It literally laid the foundation for technologies that are changing our world. Number one, quantum computing. The artificial atoms they built, those are basically the great-grandparents of the superconducting qubits that power today's most advanced quantum computers. Number two, advanced sensors. This same research allows us to create incredibly sensitive devices for everything from medicine to discovering new materials. And number three, fundamental physics. This work created a real, tangible bridge between the quantum and classical worlds, opening up whole new fields of study. And what's really amazing to think about is that this all happened more than a century after quantum mechanics was first dreamed up. It just goes to show you that even after all this time, we are far from done learning about this field. It really speaks to what the Nobel Committee themselves said about it. They noted, even a century after its inception, quantum mechanics continues to surprise physicists with new applications and insights. This discovery is the perfect example of that. So when you put it all together, from showing that a big circuit can act just like a tiny atom, all the way to paving the road for quantum computers, this work really did change the game. It just forces us to confront an even bigger question, doesn't it? What quantum surprise will redefine our world next?